Assalamu alaikum. In the last lecture, we were talking about the differential relay and we discussed about the simple differential relay in detail. So we talked about the internal fault, external fault, with and without the ideal CT employment. Now in today's lecture, we will try to remove the drawbacks of the simple differential protection scheme by using a differential scheme or a percentage differential relay. In the last case, we were only considering the relay which has an operating coil and there was a pilot wire impedance that was at this point. Now the problem with the simple differential protection scheme was that for the large through fault currents, the spill current will become greater than the plug setting after a certain value. So after this point, for the through fault, we will have the spill current through the relay which will be greater than the plug setting value of the relay. Now to remove this problem from the differential relay, we will be using the percentage differential relay, and specifically we will be employing restraining coils. This one and this one, these are the two parts of the restraining coil, which is center tabbed by the operating coil. So NR is the number of turns of the restraining coil and N naught is number of turns of the operating coil. So why do we need this restraining coil in the percentage differential relay? That is the question. What we want is that as the external fault current increases, so this is the spill current value. So as the external fault current increases, the spill current required for the operation of the relay differential protection scheme should also increase, and for that purpose we are employing the restraining coils, right? So what will be the impact of using the restraining coil? Let's talk about it in terms of equations. For example, we have two different parts of the restraining coil. We have divided it into two parts. So the number of turns in one part of the restraining coil is NR by 2 and the other one is also NR by 2, that is representing by these two values. So now if we have to calculate the magnetomotive force, that will be equal to Ni for any coil. So for this coil, it will be NR by 2 into I1 because the number of turns are NR by 2, and similarly for this coil it will be NR by 2 into I2, as I2 is the current that is flowing through this coil and I1 is the current that is flowing through this coil. So we have two MMFs in two different parts of the same restraining coil. So if I have to find the total impedance or total MMF, it will be the summation of these two values, 1 and 2. And for torque, we know that torque is directly proportional to I square. Current is directly proportional to flux. The torque is actually proportional to square of flux, right? So in order to calculate the torque produced in the restraining coil, we will be using this equation M into MMF square, because we know that MMF is directly proportional to flux, because in a magnetic circuit we have flux that is flowing through the core which is having some reluctance in the presence of some MMF. So this flux is directly proportional to MMF, and flux is also directly proportional to the current. So current is the square of current is actually directly proportional to the torque that is being produced in the system. Now let's explain the differential relay operation with the restraining coil by using the balanced beam structure. So we have two parts of the coil. This one is one part, the restraining coil. This is the second part of the restraining coil, and this is your operating coil. And this beam is actually supported by a spring. So whenever the spill current is more than the plug setting of the overcurrent relay, then this beam will move downward, and we will have a trip signal that is generated through this trip contact. But as the fault current increases, the external fault current increases, the force that is being applied by these two restraining coils on this beam is increased in the downward direction. So the torque that is being produced by the operating coil should be more than the one that is being produced by the restraining coils plus the torque of the spring, right? So as the external fault is increasing, the restraining torque will increase, but the operating torque will also increase. So torque operating should be greater than torque restraining plus spring torque. So this is the condition for the operation of the differential protection scheme, specifically percentage differential protection scheme. So we have calculated, we have the equation for the torque that is being produced by the restraining coil. We can show the spring torque by T spring, and for the operating torque we will use the same procedure, and we will get the formula m into n naught I1 minus I2 whole square, and this n naught is actually the number of turns in the operating coil, and I1 minus I2 is the spill current that is being passed through the operating coil. So this is your operating coil. So the current that is passing through n naught is I1 minus I2. So 1 is the restraining torque, that is summation of the torque of the restraining coil plus the spring torque, and the other one is the operating torque, and operating torque is dependent on the spill current. And just before the operation of the relay, the operating torque should be equal to the restraining torque. We are neglecting the spring torque right now, and we can cancel these m and squares. So I1 minus I2 will be equal to n naught over nr into I1 plus I2 over 2. So this K represents the ratio of operating coil turns to the restraining coil turns. This is known as circulating current that is passing through the restraining coil, right? So I1 minus I2 is equal to K I1 plus I2 over 2 plus K2. So this K is also known as percentage bias. We talked about the angle at which this line should be tilted, right, in order to avoid the false operation of the differential relay in case of large fault currents, right? So this is spill current and this is through fault current. So this slope of the line, in which this region is the trip region and this one is the restraint region, is actually defined by this value of K. So as the through fault current is increasing, the spill current that is required for the operation of the relay is also increasing, and the slope of this line is set by changing the value of k, and we can set it because this k is actually the ratio of n naught over nr, where n naught is the operating coil turns, r is the restraining coil turns. Right, now let's assume if we have an internal fault. In that case, suppose we have I2 is equal to 0. So if I2 is equal to 0, this I2 will be 0, this I2 will be 0, and 2I1 will be equal to KI1. I1 will cancel out and K will be equal to 2. So the slope of the line will be 200%. So the value of K will be 200%. So it means that now this line will be tilted at this angle. So this is 200% sloped line. Now this is the trip region and this is the restraint region. Right? So it can be seen that if there is an internal fault, in that case the value of the spill current will be somewhere here. But if we will set the value of K more than 2, it means this line will be more tilted. So there is a chance that there are some currents, there are some values of the spill current which will be neglected if we will set the value of K more than 2. So the maximum value of K that we can have is 2, and it means that the slope of the line will be 200%. The same thing is explained in this graph. Right? So this is the simple differential relay characteristic, and we tilted it so that we can have more stability in case of large external fault currents. Right? And the slope of this line will be defined by K, and in case of internal faults the slope of the line will be 200%, and this is the region which is the trip region in case of internal fault, and this is your restraint region for right. Now let's take an example of a transformer in which we have to apply the percentage differential protection scheme. Right? So we already know that there are some problems related to the actual CT when we are employing it into the system. So the first problem is ratio mismatch, because we have two different type of CTs on both sides of the transformer, because the voltage on both sides of the transformer is not same. So there is a chance that there is a ratio mismatch which will give rise to the spill current. Similarly, we know that there is a CT error because of I naught, the magnetization branch current. So this is the margin that is added due to the CT error, and this is the margin that is added because of the ratio mismatch of the CT. The third one is the on-load tap changer. So if we have the on-load tap changer operated in the transformer, then in that case there is a chance that we have different currents in the primary as well as a secondary that we have to compare. So in case of OLTC, the value of current for which CT is actually set will be different. So if it is either operating at one value, for example the tap set is at 1.02 and we have set the value of the CT with respect to this voltage, so there is a specific current that will be flowing at this time at this voltage value. But if now the tap is changed to 1 per unit, for example, now CT is set as per this value, but on the primary side the current will be the same, but on the secondary side we have a different current. for which CT was not set. So there is a error because of the operation of OLTC, right? So we have to consider the OLTC operation as well as CT error as well as ratio mismatch. And after that we also consider the safety margin. In case we have the values of CT error greater than what we expected, value of ratio mismatch greater than what we calculated, and the actual current that is actually flowing in the system when the OLTC is operating is different from the simulation that we had. So there is a safety margin that is kept for that. So this line is actually defining the trip and restraint region. So this is the trip region and this is the restraint region. Now in the actual settings we have this flat line in the start of the characteristic line, and this is actually representing the spring, and this is here because whenever we have a no load condition, the primary will have current, but the secondary current will not exist, and due to this condition we will have some spill current, and the differential protection scheme will detect the spill current in this case as a fault, which is actually not a fault. So this straight line is actually being used to remove the false operation of the relay in case of unloaded condition of the transformer, right? Now in case of percentage differential relay we have two settings. First one is the slope setting and the second one is the minimum pickup setting, right? So for the slope setting we have tabs available on the restraining coil. So this is 1, 2 and 3, and with respect to these tabs we can have different slopes because we know that K is actually equal to N naught over NR. So this is restraining coil number of turns and this is operating coil number of turns. So if you will change the restraining coil number of turns, it will change the value of K and you will have different slope values with respect to different restraining coil number of turns. Similarly for the minimum pickup setting you will have to use the spring. So this is actually the plug setting. So this was the brief explanation of the percentage differential relay that will be used for transformer as well as busbar and for motor and generator. But there will be some specific changes in the percentage differential relay setting with respect to different equipments. Thank you.